Hello guys, in this video I'm going to be walking you through these subtopics under dimensional analysis. What is dimensional analysis? Is a technique of obtaining the dimensions and units of the various quantities in physics that we have looked at in the previous video. So the first thing we need to look at is the basic quantities and their dimensions. In the previous video, we have discussed that there are 7 basic quantities and each of them they have their units and dimensions. So let's consider the table that helps us to analyze the basic quantities and their dimensions. So as you can see on the screen, the basic quantities, their respective units and dimensions. The first one is mass, unit of kilogram, dimension is m, capital letter M, length is meter, the unit is meter, and that the dimension is capital letter L, time is seconds, dimension of capital letter T, current is A, dimension is capital letter A, then temperature is measured in Kelvin, then the dimension is theta. Like I've said in the previous video, that there are 7 basic quantities, but the frequently used quantities in physics, we have just 5, and that is what you can see on the screen. Yes, and we also discussed that in physics, we use square brackets to denote dimension. So for example, if I write, this represents dimension. So for example, if I write dimension of mass, that is capital letter M, dimension of length is capital letter L, dimension of time is capital letter T, dimension of current is capital letter A, and so on. Dimension of temperature is capital letter, and that's theta rather. Sorry, that's theta. So now let's look at the derived quantities and their dimensions. The derived quantities and their dimensions. But before we analyze the derived quantities, let's talk about some important parameters. We have length, breadth, width, radius, diameter, and height. All these quantities, they are having the same unit and dimension. They have unit of meter and the dimension is L. They have units of meters. That means the unit of length is meter and the dimension is L. Unit for width is meter and dimension is L. The unit of radius is meter and dimension is L. The unit of height is meter and dimension is L. They are all having the same unit and the same dimension. Now, before we can talk about the derived quantities, before we can analyze the derived quantities, sorry, let me clean this. Before we can analyze the dimensions of the derived quantities, we must be familiar with their equations. If without the equations, we cannot really do anything with the derived quantities. So we are going to start by looking at area. Area, the first thing, we are going to be learning the symbols, their respective symbols and formulas as well. So area is length times breadth. Sorry. Area is length times breadth. So the area is having a symbol of A. Then length is L, breadth is B. So let's talk about the dimensions and the unit for areas. Analyze the dimension, we also analyze the units. So dimensionally, we don't know the dimension of area yet, is unknown. The dimension of length, as we have discussed before, it is L. Then the dimension of breadth is also L. Then we can say that the dimension of area is going to be L times L, and that it will give us L square. Let's talk about the unit as well. For the unit, don't know the unit of area yet, but the unit of length is meter, and the unit for breadth is also meter. So we can say that area is going to be equals to meter times meter, and that will give us meter square. Now let's discuss the second derived quantity, that is volume. Like I said, without the formula we cannot do anything. So the formula for volume is length times breadth times height, equation 2. So that be the case, let's find the dimension, and we should also get the unit. The dimension of volume is unknown yet. Dimension of length is L, there's capital letter L. Dimension of breadth is capital letter L as well. Then dimension of height is L. So we can say that dimension of volume going to be L, that's dimension of length, L times L times L, and dimension of volume becomes L cube. Let's get the unit as well. Unit, following the formula, the unit for as you can see, the unit for length is meter, then meter for height, then breadth. So volume becomes meter cube. So the unit for volume is always meter cube. In SI system, we can also have it as centimeter cube depending on the unit of length, breadth, and height that we have used. Let's look at the third quantity, that is velocity. Velocity is displacement over time. Displacement over time, equation 3. Let's work out the dimension and the unit. So let's look at the dimension of velocity. Now the dimension of velocity is unknown for now. Then the dimension of displacement is L, while dimension of time is T, capital letter T. We can insert it into the equation 3 rather. Then we have the dimension of displacement, which is this dimension, is L, and dimension of time is T. Then we have LT minus 1. Let's work out the unit. The unit of velocity. We are going to have the unit for displacement is meter, unit for time is seconds, and that should give us meter per second, which can also be written as this. So let's look at the next one, which is number 4, acceleration. But we have to be sure by confirming that displacement, velocity, and speed, they have the same unit and the same dimension. You can feel free to work it out. The only difference is that one of the difference rather is that speed is a scalar quantity while velocity is a vector quantity. So let's continue. Acceleration, the symbol for acceleration is small letter a, while capital letter A represents area, and that is velocity over time. Velocity is having a symbol of small letter v, while volume is capital letter V. That's equation 4. Acceleration, you want to work out the dimension of acceleration. That we are going to have velocity is LT is per minus 1, and time is T. Now we have said that indices is paramount, important to us in science. So we are going to have, just write the L since we only have one L, but we have two T, so we can solve it using indices. Let's take a look at it. Solving it using indices. As we have T raised power minus 1 divided by T raised power 1. How? This T that is here is having a power of 1. Then we can, since we are having the same base, we pick one of the T, then the first power is minus 1. Division in indices means minus, then the second power is 1, and that it will give us T raised power minus 2. So in short, if I solve this, we'll have T raised power minus 2. That's the dimension of acceleration. Let's work out the unit of acceleration. Unit, hold on. The unit for velocity is meter per second, while the unit for time is seconds. We follow the formula for acceleration, and since we only have one parameter here, meter, a single parameter, but we have two s, we can solve it the same way we have analyzed the t. You can say s minus 1 divided by s raised power 1, and pick one of the base, that is s minus 1 minus 1, then the indices we have minus, then the second power is minus 1, so we have s raised power minus 2. So in that case, we'll be having s raised power minus 2. So the unit for acceleration is meter per second square. Now let's look at the next one, which is number 5. We have force F, that is mass multiplied by acceleration, question 5. You will notice something, that these quantities, these derived quantities, they follow a regular trend. That means if I don't know the dimension and unit for velocity, I cannot work out that of acceleration. Now, for us to be able to get the unit and dimension of force, we must know or remember the unit and dimension of what? Acceleration. So let's look at it. The dimension first. Dimension of force, they are following the formula. Dimension of mass is capital letter M. Then dimension of acceleration is lt raised power minus 2. We have discussed that. The dimension of force is going to be lt raised power minus 2. So as from today, the dimension of force is always mlt raised power minus 2. Now let's look at the unit for force. The unit for force. The unit for mass is kilogram, while the unit for acceleration is meter per second square, and as that will give us kilogram meter per second square. So instead of us writing kilogram meter per second square, we can as well write it as 1 Newton is equals to 1 kilogram meter per second square. So the unit for force, we have 2 units for force. The first unit is Newton, which is N. Then the second unit is kilogram meter per second square. We should remember that the Newton represents the derived unit. Yes, the derived unit for force, while kilogram meter per second square represents the basic unit. The base unit for force. Now let's look at the next one, which is work. Is W as force times distance. Question 6. Let's work out the dimension and the unit. You can feel free to pause the video so we can try the dimension. Work, using make use of square brackets to indicate the dimension. The dimension of force is mlt raised power minus 2. The dimension of multiply by distance L, and that will obtain dimension of work to be equals to ml. We have 2L, that is L times L will give us L squared, then we have T raised power minus 2. So the dimension of work is ml squared T raised power minus 2. Then we can as well work out the unit for work, because the unit for force, because we are using the equation, unit for force is kilogram meter per second square, then multiply by distance meter, and work will give us kilogram meter square s per minus 2. So the unit for work is kilogram meter square per second square. As well write it as 1 joule is equals to 1 kilogram meter square per second square. So from here we have unit of joule, then we have unit of this. Now let's try to understand what's meant by the basic and the derived unit for work. The basic unit for work is kilogram meter square per second square. The derived units, we are going to have two. The first one is joule. You can as well work out another derived unit for work by considering the equation again. If we consider the let's consider another equation. Work is force times distance, and that we are going to have unit for force. The derived unit for force is Newton, then the unit for distance is meter, and that will give us Newton meter. What is the derived unit for work? So work is having two derived units. The first one is joule, and the second one is Newton meter. Now, as we can see, we have been looking at the derived quantities, their units, and their dimensions. So of all the various derived quantities that we have, we need not to memorize the whole thing. It is going to be cumbersome for us. So we just need to remember the 6 quantities starting from area, volume. We have looked at volume, velocity, or we say speed. Then we look at acceleration. We also consider force, and we have looked at work. Yes, so now there are some quantities that are complementary quantities, like work goes and with energy, then velocity goes with speed. So these are complementary quantities. So let's analyze the dimensions of some quantities in physics. Okay, so we start by looking at charge. Like I said before, if we do not know the equation, we cannot solve the unit and the dimension of these quantities. So charge is current times time. That's Q equals to IT. That be the case, let's work out the dimension as well as the unit. We start looking at the dimension. The dimension of current is a basic quantity, that's A, and the dimension of time is also a basic quantity, that's T, and that gives us 80. So that's 80. So the dimension of charge is 80. Let's work out the unit as well. The unit, we are going to have current is ampere, while charge is seconds, and that will give us ampere seconds. And as well write it as 1 coulomb is equals to 1 ampere seconds. So another unit for charge is coulomb. Coulomb is a derived unit, while ampere seconds is the basic unit for charge. Now the second one is linear momentum. Linear momentum is a vector quantity, and it's having a symbol of small letter p. That's mass times velocity. Small letter p, because capital letter P represents pressure. So let's work out the dimension. Dimension of mass is capital letter M, multiplied by dimension of velocity is LT per minus 1, and that's the dimension of momentum give us MLT per minus 1. Then let's work out the unit. For unit, there's no need for us to put square brackets. So the unit is going to be, the unit for mass is kilogram, the unit for velocity. As you can see, if you have not worked out or try to memorize the 6 quantities, derived quantities we have discussed the other time, we're able to work things out here. Multiply by meter per seconds, and unit is going to be kilogram meter per seconds. That is the unit for momentum. That's linear momentum. Yes. The next one is electrical potential, which we can also call potential difference, is defined. Let me change my ink. Is defined as the work done per unit charge. Work done per unit charge. So let's try to work things out. The first thing is the dimension, electrical potential. We don't know the dimension of work. We said it is ml square t minus 2, while the dimension of charge is 80. So when we try to solve this, we are going to obtain, return back into the equation work. Anywhere we see work, we write ml square c minus 2 over charge. Charge is 80. Now we are going to solve using indices. Since I only have one m in the equation, I only have a single m. I'll write down out first. Then I have single L as well. I have L square. Then the A is 1. A, the power here is 1. So it's going up, becomes A raised power minus 1. Now we have two t's that I want to discuss here. We have t raised power minus 2 divided by t raised power 1. The power for the denominator here is 1. So we follow law of indices. We pick one of the base, t, then the first power is minus 2. Division means minus, then we have 1. So we are going to be having t raised power minus 3. So if we solve this, we'll be having t raised power minus 3. So the dimension of electrical potential or potential difference is always ml square a minus 1 t minus 3. Let's look at the unit. The unit for work, as we have discussed, is joule. We are using the drive unit. Then the unit for charge is coulomb. You can write it as voltage, which is our electrical potential, is joule per coulomb, and that will give us joule per coulomb. So you can feel free to pause the video and try to work with the basic unit for work and charge. If you want to write joule per coulomb, we can also write it as 1 volt is equals to 1 joule per coulomb. Now, the next one is capacitance. Let's work out the dimension of capacitance, which is the fourth one. So, considering capacitance equation is charge per unit voltage. Charge per unit voltage. Let's work out the unit, the dimension and the unit as well. Dimension of capacitance, and the dimension for charge is AT, while the dimension of voltage, we have looked at dimension of voltage, as you can see, is ml square a minus 1, ml square a minus 1 t minus 3. So let's try to solve this. The m is at the denominator side and is having a power of 1. So when it goes on, it becomes m raised power minus 1. Then we only have one L as well, L raised power 2. Then it goes on, becomes L raised power minus 2. Then we have two A's, where we can solve the A's separately by following indices. Let's solve it separately. We have A raised power 1 divided by A raised power minus 1, and that gives us, pick one of the A. We are having 1, division means minus, then we also have minus 1. That gives us A raised power 1 plus 1, and that gives us A raised power 2. So in this case, we have A raised power 2. Then for the time, we have two time. Let's deal with the time as well. We have t raised power 1 divided by t raised power minus 3. We pick one of the base as well, t1. Division means minus, then we also have minus 3, and that will give us t raised power 1 plus 3, and that gives us t raised power 4. So in short, we are going to be having t raised power 4. So the dimension of capacitance is m raised power minus 1, n raised power minus 2, a squared t raised power minus 4. Just try to solve it that way. Now let's look at number 5. Number 5, which is electrical resistance. Simply call it resistance. Electrical resistance, from Ohm's law, we define it as R is equals to V over I. V over I from Ohm's law. So let's work out the dimension as well of electrical resistance. Now, as you can see, assuming we did not know the dimension of voltage, it will be kind of go to work the dimension of resistance. Since we have talked about that, it will be hard to analyze. Voltage, the dimension of voltage, we said it is ml square a minus 1 ml square a minus 1 t minus 3. We have discussed that. Voltage, then current is current dimension is a. So when we try to solve it, we'll be having, since we only have one m, we'll solve those ones first. We're having m square. We have a to a's. Yeah, we have two a's here. The first one is this. Sorry. The first a is this, while the second one is this. So looking at this, we have to solve it, and we have a minus 1 divided by a raised power 1, because the power here is 1. So we have pick one of the a, minus 1, division means minus, then the second power is 1, so we have a minus 2. So this one give us a raised power minus 2, then the t, we really have one t, that gives us t raised power minus 3. So the dimension of electrical resistance is ml square a minus 2 t minus 3. Then let's look at the unit for electrical resistance. Consider the unit for electrical resistance. Unit, the unit for voltage, we said our potential difference is volt. What the unit for current is ampere. We are using the derived unit, then that will give us volt per ampere. Instead of us writing volt per ampere, we can as well write it as 1 ohm. 1 ohm equals to 1 volt per ampere. So the derived unit for electrical resistance is ohm or volt per ampere. Don't forget, volt is also derived. So the last one is specific heat capacity. So number 6. You can feel free to pause the video to try this as well. See, that's it. The symbol is Q over M change in temperature. So let's work out the units and the dimension. Like I've said, square brackets indicate dimension in physics. So this represents heat energy. Now let me chip this in. All forms of energy, they are measured in joules, and they have the same units, they have the same dimension as work. Either electrical energy, solar energy, heat energy, mechanical energy, they are all measured in joules, and they have dimension of ml square t minus 2. You can try to work it out by using potential energy to confirm this. Then let's look at heat energy. We said heat energy is ml square t minus 2, while mass is m, and we know that the dimension of temperature is theta. So as you can see here, the m cancel m, so we are going to be left with s square t minus 2, then theta, the power here is 1, so it becomes theta raised power minus 1. So the dimension of specific capacity is L squared t minus 2, theta raised power minus 1. The last one is the unit. The unit, we have C, which is heat specific capacity. The unit for heat energy, like I've said, is joule. The unit for mass is kilogram, while the unit for temperature is Kelvin. Temperature unit can also be in degrees Celsius or Fahrenheit or Rankine, depending on the required unit. So we are going to be having joule per kilogram per Kelvin. It can also be in terms of joules per gram per Kelvin. That depends on the unit for mass. Now we have discussed the dimensions of some quantities. The concluding part is the dimensions of the dimensionless quantities. Let's look at dimensionless quantities and let's try to confirm how dimensionless quantities possess no dimension. In the previous video, we have analyzed that dimensionless quantities are quantities that do not have dimensions. So we want to work on the dimensionless quantities. So we start by looking at strain. Strain is a dimensionless quantity. Let's confirm how strain is a dimensionless quantity. Strain is having a symbol of epsilon, and that is extension over original length. So let's work out the dimension. Dimension of extension is also under length, and that is L, while dimension of original length is L. So if we try to sew it out, we are going to be having 1. And if you remember, we said that dimensionless quantities are quantities whose dimension is equals to 1. As you can see here, dimension is equals to 1. Let's work out the unit as well. The unit for extension is meter, while the unit for original length is also meter, and that if we try to cancel things out, this cancel this, and that will give us 1. So it is also unitless. Strain is a dimensionless quantity and it's a unitless quantity. So whenever you solve for strain, we don't usually write a unit for it. So let's say if I solve for strain and I'm getting answer of 20 or is 0.004, for example, there's no unit for it. Next quantity that is dimensionless is refractive index. The absolute refractive index or relative refractive index, they are both dimensionless quantity. And refractive index, which is symbolized with n, is defined as the velocity of light in air to the velocity of light in another medium. So in that case, we are going to be having the dimension as dimension of velocity of light in air is LT raised power minus 1, and dimension of velocity of light in another medium is also LT raised power minus 1. So we try to cancel things out, this cancel this, and that will give us 1. So it is also dimensionless. Let's work out the unit as well. Let's check, maybe it is unitless. The unit for velocity of light in air or speed of light in air is meter per second, while the unit of velocity of light in another medium is also meter per second. And that if we try to cancel things out, this cancel this, and that will give us 1 as well. So refractive index is a dimensionless and unitless quantity. The third one is relative density, so a dimensionless quantity, relative density. And we define relative density as density of a substance to the density of a standard substance, which is usually water. Density of a substance, density of standard substance. So from here, let's try to work the dimension and the unit. But before that, let's know the dimension and unit of density. Density is mass over volume. You can pause the video to try to work it out. And in that case, the dimension of density is going to be, dimension of mass is m, and we have discussed that volume is having a dimension of L cube. So if we try to simplify, we are having m L raised power minus 3 as the dimension. Therefore, the unit for mass is kilogram, while the unit for volume is meter cube. So that will give us kilogram per meter cube as well. So in that case, we can try to solve for relative density now by saying the dimension of relative density. We have a relative density as density of a substance, that is m L raised power minus 3. Sorry, we're supposed to have a square bracket for it to represent dimension. Then the dimension of a standard substance, which is usually water, is m L raised power minus 3 as well. So when we try to see, they will cancel out, then that will give us 1. So it is a dimensionless quantity. What about the unit of relative density? We'll be having the unit for density of a substance is kilogram per meter cube, while the unit of water as well is kilogram per meter cube. So if we try to solve these kilogram per meter cube cancel kilogram per meter cube, and that will give us 1. So we have looked at the basic quantities and the dimensions. We have considered the derived quantities and the dimensions. We have looked at some dimensions of some quantities. We have also considered dimension of the dimensionless quantities as well.